It's wild to think about, but in engineering, a single misplaced word can be just as disastrous as a misplaced bolt. Today, we're going to dig into why an engineer's most critical tool isn't actually made of steel, but of words. We'll see how precise language is literally the blueprint for everything, from massive bridges to tiny circuit boards.
So what do you think it is? Maybe you're thinking of some fancy CAD software or a 3D printer, or hey, even just a simple wrench. And yeah, all of those are absolutely essential. But the most powerful tool of all, it's something way more fundamental.
Believe it or not, it's language. The ability to communicate with absolute crystal clarity is the very bedrock of engineering. Precise words prevent disasters and build marvels, but imprecise words, well, they can lead to total collapse.
Think about it. From that first spark of an idea all the way to the final maintenance check, language is what guides every single step. It's the universal code that makes sure the whole team, from the designer to the person on the factory floor, is working from the exact same playbook. All right, let's start right at the beginning, the design phase. This is where abstract ideas get translated into concrete plans, and every single step of that translation relies on a very specific type of document, a specific use of language.
So this is kind of like the linguistic assembly line of design. It all starts with the design brief. That's the written goals. Then you get a sketch to give the idea some visual form. That evolves into a preliminary drawing, which has a lot more detail. And finally, you have the working drawing, the official locked-in instructions for actually building the thing. Each term here defines a very specific level of detail and commitment.
Of course, in any complex project, problems are going to pop up. Designs that look absolutely perfect on a computer screen might not quite work in the real physical world. So how do engineers deal with that? You guessed it, with more precise language.
Okay, check this out. This is a real-world design problem from the steel work for a ski lift. Now, the plan view on the left clearly shows 8 bolt holes. But if you look at the section view on the right, well, there's only room for 6. They just don't line up.
And this perfectly illustrates the precision we're talking about. An engineer wouldn't just say, hey, it doesn't fit. They'd report a discrepancy, a clear lack of agreement between the drawings. And they'd say the components clash. Now, clash is actually a technical term. It means two parts are trying to occupy the same space at the same time. That one word instantly diagnoses the exact problem.
So, once the design is solid, we can move on to the build phase. And here, the focus shifts to the physical stuff, the actual materials and components that are going to make up the final product. And guess what? The language has to be just as precise.
An engineer can't just ask for strong material. Strong how? They have to be specific. Is toughness what you need, like steel's incredible resistance to breaking? Or is it durability, like plastic's ability to resist deteriorating over time? Or maybe elasticity, like how rubber can stretch and snap right back to its original shape? Every single one of these words is a technical specification with real legal and financial consequences.
I mean, just look at this high-voltage cable. It's a composite, a team of materials working together. You've got the central conductor carrying the electricity, then it's wrapped in insulation, a waterproof membrane, and a tough armored outer jacket for protection. Each layer was chosen for a very specific, describable property.
And this precision gets down to even the most basic shapes. Are the pins on this plug circular, or are they rectangular blades? Is the layout linear or triangular? These simple geometric terms are the unambiguous foundation for describing every single component. All right, the design is done, the thing is built, and now we need to describe what it actually does. This is the operational phase, and it demands a whole different set of powerful, functional verbs.
And the verb you choose here is absolutely crucial. A safety valve doesn't just allow pressure to escape, it ensures that the pressure never exceeds a critical limit. A password doesn't just permit access, it actively prevents unauthorized entry. Each verb carries a very precise meaning of function and control.
But what happens when things go wrong? Because, let's be honest, they do. In the final stage of our journey, we're going to look at how engineers use language to diagnose problems and interpret faults. And this isn't just about fixing things, it's about understanding them first.
So, let's use this graph. Forget about the title for a second and just imagine this line shows the failure rate of a component over time. An engineer can't just look at this and say, it went up and then down. They need to use precise language to describe these trends and really uncover the story behind the data.
They've described the gradual increase, which was followed by a much steeper increase. Then the data plateaued, meaning it stayed constant for a while before it plummeted to 0.
This vocabulary transforms a simple line on a graph into a diagnostic report, giving clues about what caused each change.
And the precision goes even deeper. Is a problem an intermittent fault? The kind that happens unpredictably and drives everyone crazy? Or is it a systematic fault? One that happens consistently, every time, under the same conditions. Figuring out which one it is completely changes how you'd even begin to troubleshoot. One word makes all the difference.
So, as we've seen from that very first design brief all the way to the final fault analysis, language is the invisible scaffolding that holds the entire engineering process together. It really is the true blueprint.
And this is the key takeaway. The one thing to remember. In engineering, words aren't just descriptive, they are functional. They specify, they instruct, and they solve. They are every bit as critical as any gear, circuit, or beam.
In a field that is built on precision, every tool has to be maintained. So, the real question is, how will you sharpen your most important one? Thanks for joining me.